In this video, I want to talk about logic arrays. So there are two types of logic arrays that I want to cover here. One is the class of PLAs or programmable logic arrays, and the other one is the class of FPGAs or field programmable gate arrays. So PLAs are a bunch of ANDs followed by an OR array. So I think by this simple sentence, they may look familiar, and when I show you what they look like, you actually recognize them. You have seen these types of PLAs before, even though we didn't call them PLAs back then. They are being used for implementing combinational logics only, and they usually have fixed internal connections. On the other hand, FPGAs or field programmable gate arrays, they have arrays of logic elements or LEs. They are being used for both combinational and sequential logic circuits, and they have programmable internal connections. So as you can see, we have more capabilities with FPGAs over PLAs, but PLAs are also useful. So let's just take a look at one PLA. As I said, PLA contains an array of ANDs followed by an array of ORs. So if you recognize this combination, this is basically what we called a two-level implementation. When we wanted to use that to implement combinational logic functions. So basically what we have is we have an AND array that creates some implicants for us, and we have an OR array that ORs the required implicants to create the functions. So let's just say we want to create these two functions, x equals a bar b bar c plus a b c bar, and y equals a b bar. So by looking at these two functions, you realize that we have three inputs, a, b, and c, and we have only two outputs, x and y. So as you can see, we have three implicants. One is a bar, b bar, c, the other one is a, b, c bar, and finally the last one is a, b bar. So we have a, its complement, b, its complement, and c and its complement. To create the first implicant, a bar, b bar, c, I use a 3-input AND gate, and I connect the inputs to a bar, b bar, and c. So this creates a bar, b bar, c for me. For creating the second implicant, a, b, c bar, I put a 3-input AND gate, and I connect inputs to a, b, and c bar, and that creates a, b, c bar for me. And finally, for the implicant that is required for creating y, I need to have a 2-input AND gate, and the inputs are connected to a and b bar. So if we had some implicants that was shared between the two, that means that we only needed to create one example of that, and we could reuse that. Now, for creating the final functions, x requires a 2-input OR gate to OR a bar, b bar, c, and a, b, c bar. But y doesn't require an OR gate. Its output is simply a, b bar. So this is a two-level implementation that we have seen before. Also, we just called it a PLA or a programmable logic array. So as you can see, there are three numbers that are important here. Generally speaking, PLAs are represented by m, n, p. So m is the number of inputs, n is the number of implicants, and p is the number of outputs that we have. So this design is pretty straightforward, and you have seen this before. What you haven't seen is that when we are working with more and more complex functions, drawing these AND and OR gates is going to be cumbersome. So why not use a simpler notation? We can apply the dot notation that we have seen for read-only memory function implementations here too. Since we have an AND array and an OR array, and we specify it like this, we know that whenever for a horizontal line, we have several dots, that means that these dots are actually being combined using an AND gate. So this is how I can create A bar, B bar, C without actually showing the AND gate. I just simply draw a horizontal line and I put 3 dots in the locations of A bar, B bar, and C. I do the same for A, B, C bar too. C bar, B, and A. Also for A, B bar, A, B bar. So the only reason that this makes sense is that I have specified that this is the AND array. If I didn't specify that, then these dots didn't mean that we are creating implicants by ANDing these variables. If I just put an OR array, then it means that I'm ORing this, right? But since PLAs are a bunch of ANDs followed by a bunch of ORs, and I specified that this is the AND array, I know that these dots basically mean that these variables are being ANDed together. Similarly for the OR array too, to create X, I need to OR A bar, B bar, C, and A, B, C bar. So that's what I do. I have put 2 dots on this vertical line, on the interconnection of this vertical line, which shows X, and these 2 implicants. Similarly for Y, since it is only created by A, B bar, I only put this dot here. So as you can see, these dots and these dots mean 2 different things, because this is an AND array. These dots mean that all these variables are being ANDed together to create the implicant. This one, since it's an OR array, it means that all of these implicants are being ORed together. So this schematic without specifying the AND and OR array is meaningless. So that was PLAs. What about FPGAs? So FPGAs are more complicated than PLAs. They composed of LEs or logic elements that perform logic function for us. They also contain IOEs or input-output elements that are interface with outside world. We have programmable interconnection that connect LEs and IOEs. And some advanced FPGAs include other building blocks such as multipliers and RAMs as well. So as you can see, FPGAs are more advanced than PLAs. But here we just barely touch the surface. So the general layout of a FPGA looks something like this. We have a bunch of LE or logic elements, and we have a bunch of IOEs or input-output elements. So LEs or logic elements, each composed of several components. We have lookup tables or LUTs, which are there to perform combinational logic functions. We can have flip-flops, which perform sequential logic functions, and we can have multiplexers inside LEs that connect lookup tables and flip-flops. So this is a general design of a logic unit or a logic element in Ultracyclone 4 LE. So this is one logic element of Ultracyclone 4. As you can see, it looks very complicated. But for us, what is important is we have a lookup table which can accept 4 inputs. We have a synchronous load and clear logic, and we also have an asynchronous clear logic, and we have some clocks as well. So let's just take a look at one example of how we can program a FPGA like this. For us, what we do is that we just do 2 basic combinational circuit implementations. So the ultracyclone 4 logic element has 1 4 input lookup table, 1 registered output, and 1 combinational output. So let's just take a look at this example. We want to show how we can configure a logic element in this FPGA to perform the following functions. So we have X to be equal A bar B bar C plus A B C bar, and we have Y to be equal A B bar. So if you remember, we had a lookup table with 4 inputs. So for implementing X, we actually need 3 inputs, A, B, and C. So what we have, we directly connect A, B here. We connect C through this multiplexer. And then we need to create this lookup table. Basically, we create the truth table for this function. So we have data 1, data 2, and data 3. Data 1 is A, data 2 is B, and data 3 is C. And data 4 is don't care because we don't have a 4th input. So I can just simply put it at 0, or in the truth table I can put it at don't care. So since this function is the result of ORing 2 minterms like this, A bar, B bar, C, or A, B, C bar, the 2 rows for which we have these 2 minterms are 1, and all the other ones are 0. So this is basically what we store in the lookup table in one of the LEs of the FPGA to implement this function. What about the other one? Y equals AB bar. So as you can see here, this function only has 2 inputs. So with 2 inputs, we only need to use data 1 and data 2. And to create the lookup table, data 3 and data 4 are don't care because we don't have any inputs. So we can just simply assign them 0, and in the truth table, we represent them as don't care. So Y is AB bar, so only 1 minterm. So what we do is that we just assign the corresponding minterm for that row of the truth table as 1, and we put the rest as 0. The general design flow in FPGAs consists of several steps. So we usually use the CAD tools such as Altera's Quartus 2. So the first step is to enter the design either using a schematic entry or using an HDL. Then we simulate the design, and then after everything is being checked and we are sure that our design is correct, we can synthesize the design and map it onto the FPGA. We can download the configuration onto the FPGA and then test the design. Of course, if anybody is interested in this process even more, you can refer to more advanced resources on FPGA programming and design.